biochemistry. He's also a director of Yale Energy Sciences Institute. He has too many awards to mention, and he published more than 400 papers, actually close to 500. Professor Brudvig is recognized as a seminal contributor to the molecular understanding of photosynthesis and also design of artificial photosynthesis systems. His current research interests include natural and artificial photosynthesis, water oxidation, and solar fuels. We are greatly honored to have him here to present his work on water oxidation catalysis for the artificial photosynthesis. Please join me on welcome Professor Brudvig.
Yeah, is the microphone on? Can you hear me? Okay. This is working. Well, sure. Thank you very much for the nice introduction, and well, maybe I could let you say a few words before I get started.
Hi, I'm Laura Steinberg. I'm the executive director of the Schiller Institute for Integrated Science and Society, and Gary is here as the first of the year, I think, of our Schiller Distinguished Scholars, who we have invited to come and give this talk. In fact, Gary spent the entire day with us, and we really appreciate that. So this is the Schiller Distinguished Speaker Series is really one of the most prominent and important things that we do at the Institute. And it's here because we dedicate resources and our time and the time of all of you here to come and hear some of the best scientists in the world talk about energy, environment, and issues related to health. And we're privileged that GR was extended the invitation to Gary, and that Gary found the time and the interest to come and speak with us and spend a day with us. And I think this is going to be a fascinating talk. We've already spent some time together. I've learned a lot about the Yale Energy Institute, and certainly something that we can aspire to have 14 faculty also. We have 3 core faculty now, Jir, Yi, and Hanshin, and we'll have some more coming up soon. So I look forward to your lecture. Thank you, Gary.
Thank you.
And thank you, Jir, for the invitation. It's the idea to invite Gary.
Okay, well, thank you again. Very nice, and it's a pleasure to be here. So just to say a few words on, at Yale University. Here's our Sterling Chemistry Lab. You may see this little statue here. That's a statue of Benjamin Silliman. He was the first professor of natural science at Yale. I started in 1803. I can tell you the story later. Of course, this looks like some Gothic building from the Middle Ages or something. And it's not that new, but we have brand new facilities at we call our West Campus. This formerly was the research and development site for Bayer Pharmaceutical, and Yale purchased the site about 15 years ago. And we've repurposed it for interdisciplinary research. We have currently 7 institutes, one of which is the Energy Sciences Institute. And we're actually back over here, but say a little bit more about the Energy Sciences Institute, where the work that I'm going to tell you about today was done. It's exciting space. We have brand new, newly renovated space. The buildings aren't new, but the interior is all done. This was just completed about a year ago, and my group has moved into that space. And I call this interdisciplinary energy research under one roof, to take a phrase from Steve Chu with his energy hub. We have faculty from all of the schools in the departments in the School of Engineering, as well as physics and chemistry, all working in the same space side by side. And it creates a really wonderful environment for interdisciplinary research and collaborative research for a topic like energy, which is a really challenging topic and one that's extremely important for us to tackle. And it gives us an opportunity to really tackle this interdisciplinary topic. I think it's a lot analogous to the Schiller Institute, and we, as we just heard a minute ago, we currently have 14 PIs, and I'm not sure the exact number, but it's over 100. There's mostly grad students and postdocs working in the institute, and so we'll tell you a little bit about some of our work. So we're interested in solar fuels. So we have to come up with a solution to the energy crisis and global warming. We have to stop burning fossil fuels. And so we'd like to be able to make fuel using solar energy, and that's the field of solar fuels. by using catalysts that can catalyze small molecule chemistry, such as water splitting, by not reproducing biology, but by using semiconducting materials like TiO2. And this is a collaboration we started, I'm not sure, maybe 17 years ago with 4 professors from the chemistry department. Victor Batista, who's a computational chemist, myself, Bob Crabtree, who's an inorganic chemist, and Charlie Schmittenmeyer does terahertz spectroscopy. There's the 4 of us, being inspired by the sun behind us. Sadly, Charlie, some of you may know, passed away a few years ago. His work has carried on. I've been directing his research group, and they're almost all finished now. But I'll certainly talk about some of the terahertz spectroscopy that was done by his students. And so with that, I'd like to talk about 2 topics that relate to recent work, but I'm going to try to make it a little bit more basic and interdisciplinary. So for those of you who know what we've been doing, you might find it a little bit too simplistic, but hopefully those of you who aren't chemists can understand what I'm saying. And please don't hesitate to interrupt if I'm not being clear or like more clarification. So what I say we're doing is bio-inspired artificial photosynthesis. And some of you may know my group also works on biological photosynthesis. We study photosystem 2. This is a cartoon picture of photosystem 2. And this is the complex that does lead-driven water oxidation in biology. The goal in biology is not to make oxygen from water, but to store the energy of solar energy in the form of chemicals, fuels. And biology makes initially sugars, and then all biomass comes from that. And that is, of course, the source of all of our fossil fuels. It's basically stored energy from the sun. And biology learned about 3 billion years ago, if you want to make fuel, which is a reduction reaction, you have to have a supply of reduced equivalents. And on a global scale, there's only one molecule that will work, and that's water. So you have to learn how to oxidize water to produce the reduced equivalents for fuel formation. And that's a challenging reaction. Water oxidation is a complex reaction. It's a 4-electron oxidation, complicated chemistry, requiring very high potentials. One of the things that's amazing about this system is that it is harder to oxidize water than every single amino acid in a protein. So how do you selectively oxidize water when you're in a protein environment? That's a really amazing accomplishment. We're not going to try to challenge that. We're going to use materials like TiO2 that are not going to get easily oxidized. But we're going to try to emulate the basic idea. That is, we're going to use light to introduce a electron transfer reaction, creating oxidation equivalents that can drive water oxidation and reducing equivalents for fuel forming chemistry. And this is the process of artificial photosynthesis. And we're going to try to develop this using what we refer to as a water splitting dye-sensitized solar cell. And I'll show a little bit more detail on that in a minute. But of course, the key problem is this water oxidation reaction. And so our group has focused particularly on the developing catalysts and carrying out the chemistry to do water oxidation. And I'll focus particularly on that. But here's a schematic of a photoelectric chemical cell for water splitting. And there's 2 halves. There's an oxidation half where water is being oxidized, producing oxygen. That releases electrons, which can be passed over to the other electrode, the cathode, which can reduce hydrogen to the protons to form molecular hydrogen. And the end result is you convert water, very stable molecule, into hydrogen and oxygen, which when you combine, of course, are very exothermic. And so the hydrogen is basically storing the energy of the solar photons. To do this, we developed surface chemistry to attach molecular catalysts onto semiconducting oxides like titanium oxide. And to do this, we need to have chemistry to attach molecules to the surface. We need some kind of anchoring group. We need a linker that connects the catalyst and the anchor, but also absorbs visible light. Those of you who know TiO2 know that it's white, doesn't absorb visible light. And so you need to have a visibly absorbing chromophore or a dye that can absorb the visible light and mediate the reaction. So this absorber, I'll call it a linker here, would absorb a photon that is depicted by this arrow and inject an electron into the conduction band. That would allow conduction of the electron over to the other electrode and leave behind a very strong oxidizing equivalent that can we pass to a catalyst that can catalyze the water oxidation reaction. So that's the overall reaction. And today I'd like to talk about two things. First, I'll say a little bit of work about anchoring group chemistry, some of the things that we've done recently and mostly unpublished. And then I'll focus on some of our work on catalysts. This is not mostly unpublished. I'll give a little bit of an overview of how we've developed some of the catalysts, which we've been working together with people here, Dunway's group and Matthias's group and Gier's group on some of the chemistry using these catalysts. Okay, so the anchoring attachment. So metal oxide, you need a molecule that can strongly bind to the surface. So we have used in the past a variety of chelating molecules like catechol, which has this bidentate chelating group, hydroxamic acid, which is also bio-inspired. These types of molecules are synthesized by bacteria to sequester iron, and acetylacetonate, which is a well-known chelating group in inorganic chemistry. And these all have been good, but not completely satisfactory, in that they don't all have such stable binding. And one of the newer directions we've used is to use a protected siloxane. So this is a siloxane attached to a metal oxide. These are well known to be very, very strongly attached to the surface of metal oxides, but the precursor siloxane molecules are incredibly difficult to handle. They polymerize very easily. They're not well behaved. And so we've utilized a protected siloxane. This is called a silotrane, which has this triethanolamine group that protects the surface, the siloxane. It allows us to do synthetic chemistry where we can make dyes, we can make catalysts. They don't get screwed up by the siloxane. And then we can, by mild heating, attach it to the surface. So that's all been good. And this has been really of interest. But one of the more recent findings is that this protecting group doesn't actually just leave, but it blocks the site adjacent to the siloxane. And it then can be removed by an acid wash, which frees up adjacent sites that we can now put two molecules next to each other. For example, a dye and a catalyst, or two catalysts for bifunctional chemistry, so that we, instead of having just random positioning, we can have adjacency for cooperative chemistry. And we're pursuing this with Dunway right now. Actually, we're writing a grant proposal to get Dunway's doing it, but actually not. And so that's something that's been very, very interesting and exciting. But more recently, we started looking at this molecule here. This is called BODIPY. It's a dipyridine molecule, but it's got this boron difluoride group. And it's been very widely used in many applications, including biological imaging. It's a very highly fluorescent molecule. It's been used to image biological systems. And it's also been used in solar cells. In this case, however, by putting an anchoring group, here's a attached anchoring group, and you can see it's attached here is the boron difluoride group. And we were pursuing this because we thought it might have interesting light absorbing properties. But to our surprise, it loads spontaneously onto the surface and binds to the surface of titanium oxide. So these are a series of molecules we looked at. This is the dipyrin, this is the BODIPY, this is the fluorophore that's used in biology, which has a dimethyl substitution. And the reason nobody had found that it binds to metal oxides is that the dimethyl substitution blocks the binding. And you can see there's no binding of the dimethyl. But if you remove those methyl groups and remove the steric interactions, it binds just about as well as the carboxylic acid, where we now, with the dimethyl group, can't bind through this end, but it binds on the carboxylic end. This has been widely used in dye-sensitized solar cells because it binds and has nice interfacial electron transfer properties. And you can see that the BODIPY binds comparably well, which was really surprising to us. So that was something that we wanted to learn a little bit more. How is it binding? One way to study this is by using X-ray photoelectron spectroscopy, which is a technique that looks at the ejection of electrons from an element of interest, in this case boron, and the energy tells us some information about what kind of coordinating environment it has. And so this is just showing this molecule here, the BODIPY, and it has, by its itself free in solution at X-ray photoelectron spectral energy of around 193 electron volts. But when we bind it on TiO2, it shifts by about 1 electron volt. So it tells us there's a change in the boron coordination. On the other hand, this carboxylic acid derivative has a similar binding energy free in solution and doesn't shift very much. Free in solution and on the surface doesn't shift very much, which is telling us it's not binding through the boron end, but through the carboxylic end, which we expected. To probe this a little further, what we suspected was that the boron was binding through an oxygen to the titanium to form a boron-oxygen titanium bond. So we synthesized this model complex with oxygen coordination to boron. And interestingly, the model complex has an energy very similar to the energy of the Brudvig bound to titanium oxide. So we're pretty sure that the boron is bound through this oxygen linkage like this. And it's incredibly stably bound. And this is just showing the stability in water. If we soak a carboxylic acid linkage at pH 2, 7, or 10, it rapidly comes off. It's a little more stable under acidic pH, but not stable at higher pH. On the other hand, the Brudvig is bound pretty stably, even at over a pH range from 2 to 10. So this is now a really interesting situation because we've got a very stably coordinated anchoring group, but it's also a dye. So it serves two functions at once. Does it work for water oxidation? So these are some comparison of voltages for electron band edge for TiO2 and tin oxide at neutral pH. And we measured the ground state potential electrochemically for Brudvig and also the carboxylic acid version, and the excited state potential, which is done by using the absorption energy. And what we see is that the predicted potentials of the excited state are more negative than the band edge of either TiO2 or tin oxide. So it would predict that there would be an injection reaction, electron transfer reaction. And indeed, that's what we observe by using terahertz spectroscopy. So just to give you a little bit of an introduction, terahertz spectroscopy is a probe of electrons in the conduction band. And the technique we do is we excite, electrons are injected into the site with a visible photon. The electrons are injected into the conduction band, or if they are, they'll be now mobile and they absorb terahertz radiation, which is a very low energy frequency that is absorbed strongly by conduction band electrons. And so we do a pump probe experiment. We have a visible pump which excites this transition. Typically we use around 400 nanometer femtosecond, about a 10 femtosecond pump pulse. And we follow it with a probe pulse and with a variable time delay of a terahertz probe pulse. And so if the pump pulse is after the probe pulse, we don't see any attenuation of the terahertz beam. If the pump pulse is immediately before the probe pulse, we see an attenuated terahertz signal. And then if we wait a long enough time, it comes back. And this is what we see. And this is now the point time zero is when we give a optical 400 nanometer femtosecond pump pulse. And we see very rapid absorption of terahertz from all of these molecules bound on the surface, which is telling us that there's ultra fast electron transfer in all of these cases on a femtosecond timescale. And then it recombines on a much longer timescale, hundreds of picosecond timescale. So we have a long-lived charge injection with these molecules. And this is something that we've been able to also simulate. This is Victor Batista and one of his postdocs simulated using a quantum dynamics simulation, the injection reaction. What he does is he puts the electron in the excited state of the Brudvig molecule bound on the surface of titanium dioxide. Here's the electron in the conduction band. And then he simulates the transfer of that electron, which then disappears from the Brudvig orbital and appears in the titanium oxide surface. And here's a little, I think I need to use this to show this is the little movie showing the electron injection. And so here you can see it injects initially to the interfacial titanium ions that are near the surface, and then it distributes throughout the lattice in the conduction band. And this is happening, you can see, on a tens of femtosecond timescale. So this is ultra fast injection. And so this is really exciting. And just to give, and then following this, well, that suggests that we get charge injection, we get an oxidizing potential sufficient to do water oxidation, which is what we're hoping to do, but we're sort of as a first step, we did a sacrificial electron donor. This is sodium sulfite. Sulfite is an electron donor. And see, we can see a photocurrent of the light on, light off as the sulfite is being oxidized. And this is just comparing a Brudvig molecule with the carboxylic acid version. They both show photocurrent, but you can see that the Brudvig is much more stable. Although it starts out with a lower photocurrent, its stability is higher and it's not decaying significantly. The carboxylic acid version decays quite rapidly away, mostly because dissociation from the surface in water, but also from faster degradation. So this is something that's very promising. And just to summarize, we see that these now molecules, Brudvig and dipyrin, are able to function both as anchoring groups and photosynthesizers. So we kill two birds with one stone by making this. We've got both attachment to the surface and also visible light absorption, which simplifies the construction of these dye-sensitized photoanodes. And it's able to inject at an ultra-fast time scale, but also be oxidizing enough to do water oxidation. So what we're in the process of doing now is coupling this new anchoring group and dye combination with a water oxidation catalyst to do light-driven water oxidation. And that's in progress. So hopefully we'll have something to talk about the next time around. Okay, let me shift gears. That's a little bit of our recent work, mostly unpublished work on new anchoring group chemistry. Let me shift gears now to water oxidation catalysis. And just to give a little bit of background on this, when we do catalysis, we can do a catalytic reaction with a molecular complex in homogeneous solution. So this would be in solution. The advantages of this is that we know how to synthesize molecules, and we can tune them, we can do rational design. They're much easier to characterize. We can crystallize and solve structures. And oftentimes by design and optimization, we get very high efficiency catalysts in these molecular complexes. The downside is that they're often not very stable, and oftentimes are using rare metals for the best catalysis. On the other hand, heterogeneous catalysts are widely used in the chemical industry because they're oftentimes very stable. They have good earth abundance, but often the design is really more empirical. The surface may have many different sites. We don't really know which ones are the catalytic sites. It's very hard to characterize. And oftentimes the efficiency is not, and selectivity is not very good. So we'd like to be able to combine the two advantages of heterogeneous catalysis and homogeneous catalysis. Now, one comment about why are homogeneous complexes unstable, especially water oxidation catalysts, and there is no molecular water oxidation catalyst that will survive more than a few minutes in solution under catalytic conditions. And that's because it's harder to oxidize water than it is to oxidize anything organic. So these are just showing some bond association energies. Water around 119 kcals per mole. A phenyl CH bond, which is one of the strongest CH bonds, is not as strong, so it's easier to oxidize that phenyl. And even aliphatic methane is the strongest. The aliphatic CH bond is 105. So every CH bond is easier to oxidize than water. And what that means is if we have a catalyst that's capable of water oxidation in solution and it's diffusing around, it'll diffuse to another catalyst and chew it up. And that's what happens. And so typically, people report turnover numbers of 100, maybe 1,000, and they'll think that's great. Photosystem 2, which is also made of organic molecules, does more than 1 million turnovers. So it's figured out how to do that. How does it do it? It does it by keeping the catalyst away from others buried in a protein and in a rigid environment so it can't access these successful CH bonds. And that's what you can do by putting a molecule on a surface. So if you heterogenize the molecular catalyst, it's now anchored, so it can't diffuse around and chew each other up. And you can combine high stability and high efficiency. And that's what we've been able to do with some of the molecular catalysts I'll describe. So let's talk about molecular catalysts for water oxidation, homogeneous catalysts. The first one that was reported was this so-called blue dimer. It's a ruthenium dimer reported by Tom Meyer's group in the early 80s. And it was the first molecular catalyst we reported a manganese tropyridine complex in the late 1990s. You know, interestingly, in 1999, these were the only two classes of molecular catalysts that were known. You know, only two. You know, there's thousands now. In fact, probably every issue of Jaxial, somebody has another one, and they're all kinds of different types. And so there's been an explosion in this. But if you look at the elements that are used for water oxidation and molecular catalysts for water oxidation, let's start out with biology. So photosystem 2 does water oxidation, more than 1 million turnovers. It uses manganese. I would argue that nature had the choice of any first row metal. These are the earth abundant elements. It picked manganese. And so I would say manganese is probably the best choice of a first row element for water oxidation. Another thing we have in inorganic chemistry is what's called the diagonal rule. So those of you who took introductory inorganic chemistry may have heard this. That is that if you want the element in the second row has the most similar chemical properties as the first row, you go down to the second and over one. That's ruthenium. By far and away, the largest number of water oxidation catalysts that are known are based on ruthenium. The first one from Tom Meyer was ruthenium. If you go down one more row and over, it's iridium. So it had been known for decades that iridium oxide is the best heterogeneous water oxidation of all the metal oxides. That had been reported many decades ago. But until quite recently, no one had made a molecular iridium complex until Stefan Bernhardt reported this in 2008. So that's not that long ago. This was this iridium phenylpyridine complex. And that got us interested in iridium as a molecular water oxidation catalyst. However, what we want is something that is oxidation resistant and stable and stabilizing high oxidation states. And we explored a variety of different kinds of complexes. And this ligand, the so-called pi-alk ligand or pyridine alkoxide, this is the name of it, if you want that full chemical name, has been the winner. And it combines some very good properties. It's a strong electron donor, so that helps to stabilize high oxidation states. It has very good solubility. It very strong and rigid binding. It has this chelating group. It's oxidation resistant. And it also combines this alcohol group, which can dissociate a proton in a high oxidation state. So it can carry out what's called proton-coupled electron transfer, which helps to modulate and make easier the oxidation reactions. So we've been exploring using this pi-alk complex. I'll tell you about some iridium chemistry now, which is more historical, but we're also working a lot with first row metals, and copper in particular has shown very good performance with pi-alk. And so the complex that we worked on with iridium was based on this precursor. It's a iridium with this pyridine alkoxide coordinated to it. We put on initially this pentomethyl cyclopentadienyl group, thinking it would stabilize the high oxidation state. And it turned out that's just a precursor because this group is oxidatively degraded, and it, either using electrochemical oxidation or chemical oxidation, we form this so-called blue solution, which is an iridium dimer. This is a modeled structure of it, which is a phenomenal water oxidation catalyst. I'll show you in a minute. And this is sort of showing here, if we take the precursor complex and turn on a potential of 1.6 volts, which is high enough to oxidize water, we see no water oxidation. This is looking at oxygen that's evolved. But if we make this blue solution, you can see very high rate of oxygen evolution. So it's a very effective water oxidation catalyst. So this is the blue solution. It's stable. Make it, put it on the benchtop, room temperature, stable for weeks. So it's a very stable molecule. We know that the CP star group is lost. It's oxidatively modified. There's no nanoparticles being formed over time. And as I mentioned, very active for water oxidation. And we know it still has the chelating group because the absorption depends on which chelating group is put on other ones. And so this solution, however, has been incredibly difficult to characterize in detail. So the solution species, I should go back, that we make, this blue solution here, is actually not one compound, but it's a mixture of a lot of different closely related compounds that have, we presume, different proximity, the spatial arrangements of these coordinating groups, different terminal ligands, and so on. We modeled it using a combination of spectroscopy and computational modeling. The computational modeling was done in Victor Batish's group. The X-ray analysis was done with Dave Peavy and Lin Chen at Argonne National Lab using XFs and high energy X-ray scattering, and computational modeling means you can show some of the modeled signals here. We came up with this flow structure, which is a diiridium monoxyl bridge structure with these coordinating waters that can form internal hydrogen bonds that form a stable structure and leave open coordination sites that can presumably still be available for catalysis. So that is the catalyst. What we want to do is put it onto a surface so that we can heterogenize it, make it more stable, as I mentioned. And this is work that was done by Staff Sheehan. So Staff is a Boston College graduate. He did his undergraduate degree here and worked with Dunway, and then came to our group to do his PhD at Yale. And I can tell you afterward, but has gone to greater, bigger, and better things. He started up a company called Air Company now, which is making sustainable jet fuel and ethanol. And he's been named Forbes 30 under 30, best 30 under 30. He's been in the C&E News as young whippersnapper and everything that they have. So he's gotten lots of PR. But while he was with us, he showed that this blue solution species binds spontaneously and very tightly to all variety of metal oxides. And so here's some examples: titanium oxide, tin oxide, tungsten oxide, iron oxide. Here's the blue solution. We made that using this catalyst activation step I mentioned. It's a stable blue solution. We just soak a film, a mesoporous film of these metal oxides, and it binds to the surface. So there's a TiO2. It's incredibly tightly bound. In the case of TiO2, we found that we can't strip it off except using conditions that dissolve TiO2. So it's basically grafted onto the surface as part of the oxide lattice. And so it's really tightly bound. And it's an incredibly good catalyst even when it's bound on the surface. So this is now using a conducting metal oxide, nano ITO, or Indian tin oxide, which is a conducting oxide. This blue solution catalyst will bind onto the surface, and we can then carry out cyclic voltammetry, in this case at about pH 2.6. And what we see if we carry out a cyclic voltammogram, we see a pre-oxidation, which we attribute to oxidation of iridium-3 to iridium-4, and it's pretty reversible. And then we see the onset of a catalytic wave, which happens essentially right at the thermodynamic potential. This is really amazing. Normally, when you have a water oxidation catalyst, you have to stand to a much higher potential. This is referred to as the overvoltage in a reaction, typically hundreds or maybe even 500 millivolts. So this is really the onset almost at the thermodynamic potential, very low overvoltage, and it's incredibly stable. So this is some work also from Staff. He did X-ray photoelectron spectroscopy after about 100,000 turnovers, and looking at the iridium XPS signal, the nitrogen XPS signal, which is coming from the ligand, and the carbon XPS signal also coming from the ligand. And these XPS signals are virtually identical to what they were before the catalysis. So the complex is very stable. The ligand is still bound, still molecular. There's no measurable degradation, even after 100,000 turnovers. We actually carried out an electric catalysis for a month, and it would maintain catalytic activity for a month. So this is, I think, an illustration of what I said before. By heterogenizing these catalysts, you now overcome the problem of instability because they can't diffuse together and chew each other up. So can we do a light-driven water oxidation? So I'll tell some old work with Dunway just to illustrate this. What we'd like to do is put the catalyst on the surface of a metal oxide, shine light on it, and drive over a water splitting reaction. And this is work that was done with Dunway. It was published quite a few years ago, putting it on hematite. And you can see that when it's bound to hematite, the photocurrent occurs at a lower potential, so it's improving the photooxidation, water photooxidation. It shifts by about 250 millivolts. by binding this catalyst on the surface. And Dunway's group also made a full water splitting cell. This is by combining the metal oxide with the rhodium catalyst on it with as a photoanode, which absorbs the short wavelength, blue and shorter wavelength visible light. The longer wavelength passes through and is absorbed by a amorphous silicon photocathode. And you can get complete water splitting, oxygen evolution on the anode, hydrogen on the cathode, and with essentially 100% Faraday efficiency with no bias voltage. So this is exciting. And it works at pH 1, which is really kind of one of the holy grails for water oxidation, is to have systems that work under acidic pH. And that's because oxidizing water creates protons, which drives the system toward the acidic pH. So if it doesn't last under acidic conditions, you might have trouble to do water oxidation, photochemical water oxidation. And this is also, with Dunway, it was possible to image the surface of the hematite, and we can see these spots of higher density. This is sort of standing along between these two stars. And what we see is these two iridium atoms next to each other, only dimers. So the dimer bond of the surface remains as a dimer. There's no breaking apart, no forming of nanoparticles or anything. And because we can see the lattice structure, this allowed Victor Batista's group and Yang, who's the real expert on computational modeling, to model the structure of the surface using the hematite lattice and the iridium on the surface. And this is a computational model, which looks something like this, where we've got not only stable anchoring of the iridium using the oxygens to the lattice, but also water coordinated as terminal ligands, which are we believe the active sites for the water oxidation reaction. And what you can see is that this dual heterogenized catalyst, or DHC, improves dramatically the photocurrent as a function of potential compared to bare hematite or iridium nanoparticles or single iridium atoms, and dramatically improved over those other systems, despite the fact that, as I mentioned, iridium nanoparticles, iridium oxide is the best known heterogeneous catalyst that has been found. So this is significantly better. And it can do a lot of chemistry besides this. And so that's something that we've been exploring, but I'll finish by just saying a little bit about how does it do? What is the mechanism, this reaction? And one of the reasons we're interested in the mechanism is if we understand the mechanism, it gives us an avenue to optimize the performance. And just give you a little bit of background. This is from some work that was done by Tony Lobet on using ruthenium complexes. One nice thing about ruthenium is that the bonds are very stable, strong bonds, and so you can label the oxygen, ruthenium complex with the isotope and put it in water with a different isotope and carry out the labeling experiment to determine where the oxygens came from. Did it come from the labeled oxygen, or did it come from the solvent? And this is two examples. One is referred to as a nucleophilic attack mechanism. And let me just take you through it. Here is the high valent metal oxo species, which is attacked by the solvent in a nucleophilic attack to form an O bond. And in this case, one oxygen comes from the oxo group, one comes from the water molecule. So the oxygen that's evolved has one of each label, which is a diagnostic that one was from a nucleophilic water and one was from the oxo. There are some ruthenium complexes that have side-by-side oxos, like this one, and they can form an internal oxo-oxo coupling reaction. And now both of the oxygens are labeled, and that's because they both came from the complex and none from the, even though the solvent has a different isotope label, it's not incorporated into the oxygen. So these are two sort of, I would say, classical mechanisms for water oxidation. So-called water nucleophilic attack mechanism and the oxo-oxo coupling mechanism. One of the things that Dunway found, which is really interesting, is that there may be different mechanisms depending on the potential of the system. And this is some work that was done with the cobalt oxide catalyst. And what was found at low potential, we have one mechanism, and at high potential, a different mechanism, which was done by varying the water activity and seeing different isotope effects in low and high salt concentrations. And this was modeled by Yang. Here's his picture now. He's the guy who does all of our computational modeling, and or at least a lot of it, but postdoc with Victor Batista. And what he found was that there was a low potential pathway which involved a lower oxidation state of the cobalt complex, which could form an O bond through hydroxyl coupling. And that this had a lower overpotential because you could do it at a lower oxidation state, but was slow. But if you could go to a higher oxidation state to generate a terminal oxyl like this, it could do a water nucleophilic attack and form an O bond. And this required a higher potential, but much faster kinetics. This, I think, was really exciting to me because it provided a viewpoint of how biology might do this. So let's talk about biology for a second. And that's my other passion is how does biology do this? So biology doesn't have the option to just turn up the potential, right? It doesn't have a voltammeter. You can't just crank up the voltage as high as you want and make it go faster. It's a very limited potential, and it's quite a low over potential, actually lower than the potential in this system here, even to do it. So how does biology do it then? How does, if it has only a low over potential pathway, you'd think it chooses the lowest over potential mechanism and then tunes the kinetics by second shelf, by putting amino acids, modifying the structure. And I would argue that biology does it this way. And this is something that we're working on right now with Victor Batista's group to model the mechanism in Photosystem 2. And it's still work in progress, but I'm quite excited about the possibility that this might be a new mechanism that has not actually been discussed at all in the Photosystem 2 community, but was inspired by this result from Gunway's group on cobalt oxide. So a little bit of the conclusions. How am I doing? Okay. For water oxidation catalysis with these atomically defined active sites on these nanostructured materials. And so how do we do? So we can make a molecular catalyst, we can design and optimize it, which we did with this iridium dinuclear complex. We can characterize its structure and function in homogeneous solution. We're still working on that. I have a postdoc who has synthesized a blue molecular complex, which we think will be the first time we can get a crystal structure of this. On Friday, we had a crystal. She came to my office and said, it's not a good enough crystal. We can't get the structure yet, but we're working on it. So maybe soon we'll have a crystal structure of this blue dimer. But nonetheless, it allows us to characterize in homogeneous solution. We can now, using an anchoring group, to attach it to a semiconductor surface and by heterogenizing it, create a much more stable system that can be used for light-driven water oxidation. And this heterogenized molecular catalyst can have very high stability. So that's, I think, where we're going now. I want to just close with a quote from Jules Verne. Some of you might have read this book by The Mysterious Island, which was written in 1870, 150 years ago. And what will we use instead of coal? Water, replied Cyrus Smith. Water? Yes, water, but split into its elements, hydrogen and oxygen, replied Smith, with no doubt by electricity, which will have become a powerful and versatile force for hydrogen and oxygen's composition will provide an infinite source of heat and light on an intensity unknown for coal. Water is the coal of the future. That was very forward-looking 150 years ago. We're still working to do it, but we're getting closer than we were then. So I was going to say a little bit about work we're doing with Dunley, but I think I'll just move on to thank my collaborators, particularly my collaborator Victor Batista in computational work, our solar group, Bob Crabtree and Charlie Schmittenmeyer, of course, the collaborators, Dunley and Matthias. Really excited about work we've done and continuing to work together. And I won't go by name, but I mentioned many of them, but these are current and past group members, students and postdocs in my group. And here's a picture of my group, at least as it was about a year and a half ago. And this is our solar group. The last picture we took before Charlie passed away. So that was a few years ago. And thank, of course, the Energy Science Institute, where the work is being done in the Department of Energy, who's funded it. And thank you for your attention. And I'll be pleased to answer any questions.
Let's first take the question from the students and the postdoc. Don't be shy.
So at lunchtime, there were lots and lots of questions. So yeah. So
Okay.
So in one slide, you show that the switch of different mechanism of water oxidation in electrochemical conditions. And you mentioned that one was possibility that the natural photosynthesis could go through lower barrier entry one. So is there any possibility that the nature can also go through switch different pathway under different conditions?
Yeah, that there's actually that's been suggested, and I don't know. It's not impossible. My view is that biology has a very limited potential that it can use. It makes a charge separation. It creates a hole about 1.2 volts, and that's the highest potential it can generate. It can't do it anything higher. So you have to go out through the cycle with 1.2 volts, which is relatively modest potential. I would argue that it's going to be hard to do a water oxidation reaction with that potential. So probably not a higher potential, but faster reaction like this. Whether this is the mechanism in biology or not, I can't say for sure, but I think something like that. And whether or not another mechanism can happen, I don't know. I would expect there is a best mechanism. And then if there's another one, it may be not as good. So probably doesn't use the less good mechanism, but I think this is a very active area right now, and a lot of controversy and still to be determined.
So benefit a lot from this presentation, and I did have some questions. So we know that the molecular catalyst usually was using as like a model reaction to revealing the mechanisms of the water oxidation, and we can extend the mechanisms to the hygienic system to help us to understand the hygienic catalyst. But we all know that, so for example, in the hygienic catalyst, there's some like mechanism different from the molecular catalyst systems, like especially there's one is a hygienic system and the other is a homogeneous system, like the O-bond formation. So for the hygienics, so there's a pathway like the two mental also species coupling, and in the molecular catalyst, especially the homogeneous systems, it's more like the radical coupling together. And we know like there's a promising direction, like we like deposit the molecular catalyst under like a electrode and to realize the high efficient hygienic system. But how do you think about the mechanisms on this kind of the catalyst? Is more similar with the molecular catalyst, like the homogeneous, or it's more like the hygienic systems? So is there a possible like some new pathways, mechanisms for the water oxidation on this kind of the catalyst?
Yeah, I think it's hard to say definitively for sure, but my view is that heterogeneous catalysts have sites for catalysis that really look like molecular sites. They're a few atoms next to each other, like two cobalts adjacently. This is not a molecular catalyst here. This is a cobalt oxide heterogeneous catalyst. But I view it as a molecular system, and like a molecular system, in that you couple O bonds from adjacent coordinated hydroxyl groups or oxo groups, or maybe by water nucleophilic attack. So I think the mechanisms that you see in heterogeneous catalysis are going to be very much the same or analogous to the mechanisms you see in molecular systems. And the question is, understanding the sites where catalysis is happening, define the molecular structures. That's very hard to do in heterogeneous catalysts. But I think if we get to that point of being able to visualize those structures, they'll look a lot like the molecular catalysts. And I think there's only a limited number of mechanisms that are going to operate. And of course, it's going to depend a little bit on how you do catalysis, whether you have very high overpotentials, very high temperature. So for example, in metal oxides, these oxo groups are going to be less likely to be involved in reaction at room temperature because they're stable, very strong bonds to the metals. Whereas at higher temperature, they become much more possible reactivity. And in fact, you can change the oxidation state of metal oxides by just heating them at high temperature and burning off, blowing off oxygen, which then, reduces the metal, or the other way around if you want to go to oxidize. So I think there are various different kinds of processes that can happen, but it will be very much dependent on the conditions you use. Biology is room temperature, no high temperature, no high potentials. So I think there's probably a very limited number of ways you could possibly do the chemistry. And just bring home this point, a lot of times when people are doing electrochemical water oxidation, they're using potentials that are pretty high. These are potentials up in the 1-2 volt range, and that's potential of 2 volts. You're not going to get that happening in biology because it just can't go, can't generate that high of a potential.
And the following questions for this, we know we can load in the molecular catalyst on the electrode, and after that we can remove the ligands and to generate a single atom or the two core of the iridium like this of the type of the active set, and we also can keep the ligands on there. So do you think the ligands play some roles and you have to decrease the barriers or change the mechanisms of the water oxidation?
Yeah, absolutely. I think that's how enzymes work. That, because you've got the flexibility or the variability of what the surrounding environment is. They can have proton acceptors, proton donors, various hydrogen bonding interactions that can tune the reactions and optimize the rate of the reaction and maybe minimize the overall potential. We're just getting the very beginning of that in water oxidation in synthetic catalysts. There's been more progress for hydrogen evolution catalysts by using second shell effects. And Dan Du Bois, for example, some of you may be familiar with his hydrogen evolution catalyst, where he uses hydrogen proton donors and acceptors that can help enhance the reactivity. I think we need to develop that for water oxidation. We haven't really been successful to do very much in that way, but biology has. I think we can learn a lot about how to do it better by looking at how biology does it.
Thank you. And I have another question about the first part, the plantations. So I'm not really familiar with that part. I just I remember so if we just change the function group of the dye, so we can shift the HOMO and the LUMO level there. So because I saw so the conductive band of the TL2 and the dyes is very close. So is that possible to change or modulate the function group and to make that gap a little bit bigger? So if it is bigger, is that possible to accelerate the charges transfer or suppress the back electron transfer?
Yeah. So one of the things we've done a lot of work, and many others in the field, is by modulating. This is for DIPI, but it's been done in a lot of other molecules, porphyrins and other types of molecules. By putting electron withdrawing or donating groups around the periphery, you can change the gap here. You can make this larger or smaller. For example, electron withdrawing groups will make it harder to oxidize. So you'll make this potential, push this down, and also change the energy between the HOMO and LUMO. So there's been a lot of work. The organic, photochemists have been working on this for decades, and there's a lot understood. And you can move these up, the HOMOs and LUMOs up and down to tune the energies to match here or do better here. And so, yeah, there's a lot of possibilities to optimize this. And in this case, for example, we've got a reduction potential or excited state potential that is pretty nicely matched to inject electrons into TiO2. It's pretty close, but slightly more negative. This is probably too oxidizing, really. And what the consequence of that is that the energy here is too high, which means it doesn't absorb as much of the visible spectrum as we'd like. So if we could optimize this, we might want to move this potential up to maybe around 1.2 volts and leave this one the same. And that's easier said than done. But if you could do that, you should absorb much more of the visible spectrum and still have it functioning. So that's something that's, a design for the future. Right now, this is where we are.
And the final question, I'm just curious about, so the bending function group are different. If that affect the electron transfer efficiency and the rate of the charge transfer.
Well, how it's bound to the surface?
Yeah, because you're showing the two different, not just the two, several different ways to bonding with the, yeah.
Yeah, maybe I should go ahead here to this picture. So this is the quantum dynamics simulation. What you see here is that the orbital, this is the excited state orbital is localized on the part of the molecule that's near the surface. And that's a good thing because that means there's good coupling between that orbital and the surface conduction band orbitals. So you get very efficient electron injection, which is why this happens on a very fast 10 of a second time scale. On the other hand, if you had the excited state orbital on this end of the molecule further away from the surface, it would be less efficient to do that. And also, bonding to the surface makes a big difference. If that bond creates a couples the electrons on here and here, you're going to get a much more effective reaction. And let me come back. I didn't mention this. But one of the things we see in the absorption spectrum when this Brudvig is bound is we see this broad absorption. That's not from light scattering. That's from coupling of the excited state of the Brudvig orbital with the conduction band of the metal oxide. And we studied this quite a lot. We thought, for example, it was breaking the molecule of doping boron into the lattice. Not that. It's because there's very strong coupling between the boron and the conduction band, which is also helping to promote very ultra-fast charge injection in the system. And that's actually quite rare. And although on TiO2, the injection rate is, charge injection rate is very fast for all of these molecules because it's just much faster on TiO2. When we put it on tin oxide, it actually slows the injection down. And what we see is the carboxylic acid is much slower to inject charge than the Brudvig. I think that's because the coupling between the boron and the conduction band electrons much stronger for Brudvig than it is for the carboxylic acid. And that's good. So this is actually injecting better than a carboxylic acid derivative. And so that's something that, again, is an important design aspect if you want to make a system that does efficient photochemistry and interfacial electron transfer.
Thank you very much. Again, it's a very great presentation.
Thank you for the talk. A follow-up question on the heterogeneous homogeneous catalyst. So most of our work relied on chemical anchoring strategy by introducing covalent bond into the system. So I was wondering if it's possible introduce non-covalent strategy by such as pi stacking to accelerate the charge transfer kinetics.
Yeah, it depends on the system. So there's been a lot of work with graphene or carbon nanotubes where pi stacking is the preferred method to attach molecules. And they take, for example, pyrene, which is a flat organic molecule, and use it like a foot. And it pi stacks onto carbon nanotubes very tightly. And so you don't need covalent linkage there. You can just use pi stacking. Doesn't work very well with metal oxides. That kind of interaction is not very efficient and doesn't really stand up very well. So it's not stable. What we found for metal oxides is the best kinds of linkage are linkages where we make metal oxide bonds like this. And the ones that are most stable, the two that we found have the best stability are this boron oxygen and then this silicon oxygen. Those are the two best ones. They hold up and very stably bound over a very wide range of pH. They basically don't come off the surface in water, which is what you, of course, need if you're going to do water splitting.
Questions from the students? Not, open the floor to faculty and staff.
Yeah.
The ODP result. Can I see the XPS again? Yeah, here. So is this a, when you put it on the surface, do we see this is a blue shift or
So this, it's a little bit higher energy,
okay.
and it's a little bit hard.
So the blue one is the original molecule.
This is the oops, I got the blue. This blue one is this
I see.
catechol one. It has two oxygens coordinated. Fluorine, my interpretation, fluorine, like it's up here, is more electronegative, and it's a little bit harder to pull an electron out of boron when fluorine's bound than it is with oxygen.
We're not comparing this from the free molecule.
So this is, there's two comparisons. One is the free molecule with the bound molecule, and you see the shift in the XPS.
So this is where I got confused. Actually, the molecular dynamic simulation shows that the electron is moved from the molecule to titanium oxide. That's
Yeah.
oxidation, right?
Yeah, but that's a different experiment. There's no light here. There's no charge injection. It's just the X-ray photodissociation energy.
Right, but then what I'm trying to think is that, okay, so that only happens under excitation.
Yeah.
So because here the shift is not insignificant, it's over 1 electron volt. So
It's about, but this is not unexpected. So we see the shift also in this monocomplex where we just change the coordination from fluorines to oxygens.
very interesting. Because I would think that oxidation will make the binding energy shift to the higher energy.
Well, it's not oxidation. There's no oxidation here. It's just the electron withdrawing of fluorine compared to the electron withdrawing of oxygen.
It's less electron withdrawal.
It's less electron withdrawing, so it's a little bit easier to pull an electron out of boron
I see. Okay,
than it is with fluorines bound.
that makes sense. Okay.
But this is pretty well understood, and you can actually differentiate by XPS the binding environment of different elements because electron donating or withdrawing groups shift the energy up or down.
Okay, great, thanks.
Hello. So in your molecular stimulation, you have one oxygen and one F bound to the molecule, right? And here, your model actually fits better when there's two oxygen on the boron.
Yeah.
So I mean,
We don't, this is a good question. We don't know for sure. And the reason we drew it this way is partly because when Victor Batista's group did some simulations, it didn't look as easy to get both fluorines bound to oxygens on TiO2.
because the oxygen is too far
away.
Okay, that makes
But
sense. Okay.
it's very possible, and so one thing that I mentioned, I didn't mention, but I showed this is the stability of binding. So we soak it in water and we see that part of the Brudvig comes off pretty fast and then the rest is stable. One hypothesis, just as a hypothesis, is that this faster dissociating one is the one that has only one oxygen, and the one that's stable has two bound to the surface. We don't know that for sure, but it does actually fit a little bit better, as Dunway pointed out. This one is actually pretty close, better match to the one that has two oxygens bound rather than only one. So we don't really know the structure on the surface, and the reason we put this here was simply because of computational modeling. Didn't look like it fit really well, but we could easily imagine two oxygens on a single titanium, for example.
Yeah.
That's not the structure of the lattice, so we were using lattice oxygens, but it certainly could be forming on the surface, even though.
It'd also be at the grand boundary.
Well,
Yeah.
So, I mean, I'm just wondering my understanding is that the Brudvigs are so popular because they're so robust. The boron-fluorine bonds, they stay intact in whatever environment they are. So how did you guys synthetically coax it to make the exchange?
Yeah, so we didn't have to do anything.
It's just automatic, really?
We just soak it overnight. It binds it spontaneously. The surface, it depends a little bit on how you treated the titanium oxide. So we treat it with acid first. So it's kind of maybe promoting the chemistry. These fluorines are pretty stable in water, but they're not stable under really acid or basic conditions. So they can be substituted. And if you've got a nucleophilic hydroxyl on the surface, you could easily imagine attacking the
By
boron.
way of mechanism, then if there's a neighboring oxygen, it should go onto it because of the neighboring effect, right?
Maybe, yeah.
So it is, but I do understand the concept when the OHs are just apart.
This is something we debated and argued in group meetings many times and for a long time. We really don't know whether it's this kind of
It's
structure.
fantastical because that leaves the position that the arrow open for all the sorts of tuning you're gonna have. So,
Yeah. Yeah. Yeah, I actually think it might have two oxygens bound. Bob Crabtree doesn't like two oxygens because of the structure on the surface, but it does fit better with this model complex. So we'll see. We've been arguing about that for a long time, but it's a really good question.
Yeah, on the XPS as well. So for the iridium complex, you showed two signals.
Yeah.
But in the ChemDraw, you drew two iridium 4s in a similar
So
environment.
those are two different transitions.
So because I couldn't need just one.
Those are not two different chemical environments, but there's two different types of XPS transitions.
Okay, that makes sense.
And so that, yeah.
So in regards to the questions that were just asked about the coordination state, so the terahertz spectroscopy, couldn't that tell you, wouldn't you expect two different rate constants of charge injection if you had, because the simulation, it didn't look like this, right? If the molecule was tilted quite a bit. So if it's bidentate versus monodentate, so is this done in solution or with it's in solution?
It's not done in solution. So it's soaked in a solution, but then you can't pass terahertz through very much water. So we dry it down. This is actually in a dried film that's been sensitized with these molecules.
But it has seen water, so you might still have, if you have if you have the two different absorption configurations, one may already have been absorbed.
This may well be exactly what we see because this is in TiO2 and it's ultra fast, so this is instrument limited here, so we can't resolve kinetics. But when we do it on tin oxide, we can resolve the kinetics. It's slower. And it doesn't fit to a single exponential. In fact, it fits really best to a stretched exponential, which is a model that represents a distribution of rates. So it may well be that we do have these heterogeneous injection rates, that there's some that are faster and slower. And that's not really what we see in this simulation. This is pretty close to an exponential here. Maybe a little bit stretched, I don't know. But it's a single structure. And it may well be that this structure is only one of many on the surface, and that the different types of structures have different injection kinetics. I think that's almost certainly true.
And then the other question I had would be your injection, right? So there, the boron-based one injected more charge, it had a larger delta.
So, well, these are the green amplitude. So
yeah,
there's several factors that influence this. One of them is the absorption cross section. So we're not trying to. These are not normalized. These are just 3 samples, and there's differences in how much is bound. So the dye loading isn't exactly the same. So it's more dye loading. There's also differences in the absorption at 400 nanometers. We're using a 400 nanometer pump pulse. This one absorbs 400 nanometers better than these ones do. So we're getting more injection, partly because it just absorbs more of the light. And I wouldn't compare these amplitudes, exactly. It's not like this one is twice as good as this one.
But in the actual performance test with the light, the carboxylic bound compound performed much better. Initially
much better.
So can't you have just that compound in solution so you get an equilibrium and you just maintain a certain surface concentration?
That probably would work. So that would certainly mitigate the dissociation in water that occurs because of the carboxylic acid is not very stable in water. So we make the sample, we load it up on the surface, then we put it in water and it starts coming off right away.
And what about going to a different solvent? If you do water oxidation, you don't need to have 100% water, right? You just use a different solvent.
But the problem is if you put it in another solvent that's a hydrocarbon-based solvent, it's going to oxidize that instead of water. And so it's not so simple. And we went around and around trying to find a solvent that doesn't get oxidized. And maybe liquid xenon or something would work. I don't know. But anyway, it's not so true. But anyway, my main point is don't take these differences in amplitude as differences in efficiency. I mean, they're all ultra fast. They're all instrument response limited. And that's really the main take home point. the amplitude is dependent on the type of sample and spectral properties and so on.
So instead of asking a question, because you got enough questions today, particularly earlier with the students, I'd like to share a very small story that is related to iridium, this blue solution.
Yes.
So about like more than 10 years ago, I was a postdoc working for ANSWER, right? It's DOE supported energy research frontiers research center named the ANSWER Argonne Northwestern Solar Energy Research Center. So I worked a little bit with Professor Brudvig on this iridium complex. And that was actually the first time Dunway gave a talk and answer. That's the first time I met Dunway. And now after more than 10 years later, my collaborator at Argonne National Lab, who's my very fruitful collaborator and long-term collaborator, Xiaoyi Zhang, we together plan to develop a new technique, the spectroscopy technique, to study the mechanism for water oxidation. And we'll work with Dunway and using this iridium atomic dispersed iridium catalyst as the model compound study. Just want to share this small story to reflect how interesting this iridium complexes are. Thank you. Please join me. Thank Professor Brudvig.